Okay, so we've got another nice concept to connect to angles. Um, we're going to talk about the difference between linear and angular speed and how to connect these two, and we'll do a couple of examples with them. So linear speed is something we are uh, all pretty familiar with, right? This is stuff like miles per hour or meters per second. What are we measuring when we measure linear speed? Is how much your position changes. I was here and now I'm over here, right? Well, angular speed is a similar idea except dealing with angles. So our units will be things like rotations per second or degrees per minute, or let's say radians per second, right? So some linear speed, you have a unit, a measure of distance over a measure of time. Here we have a measure of angles over a measure of time. How much does your angular position change as time changes? Okay, so one thing to note about this, right? If me and a friend are in a car and the car is traveling at some linear speed, we're both going to have that same speed. If the car is traveling 30 miles per hour, we're going to be going 30 miles per hour. Angular speed is a little more complicated, right? So imagine, and we'll do a more detailed example of this in a moment, but if there's a spinning object, right? So let's say this object has some radius r, and like a merry-go-round that children might be on, right? If there's one child sitting here and another child sitting here, as this merry-go-round spins all the way around, I know those circles aren't great, the child towards the center, while they both moved all the way around, one rotation, 2 pi radians, 360 degrees, you can see the child towards the outer edge traveled further, right? So these ideas are a little more complicated. Their relationship to each other can be a bit complicated because in this example, these two children would have the same angular speed. Each one is covering the same amount of angles in every minute or second or whatever we're talking about, but at the same time, their linear speed is going to be quite different. You get the opposite relationship. Let's say I have like a bike chain. This is a pretty terrible drawing, right? So if you ever look closely at how a bike works, right, this would be the bigger gear here. So I haven't really drawn the gears. These are the gears. This is terrible. As it spins, moves the chain, right? So this is the one that you would pedal, the larger one you pedal. And as you move, you're pushing that chain around, right? So the chain we can think of as linear speed here. How many inches of chain move by in every second, okay? But if you can imagine, let's say maybe this front gear is 12 inches around. So if you pedal all the way around in 1 second, that means the chain moves 12 inches per second. Well, maybe this gear in the back is only 3 inches around. It's a small one. So in 1 second, 12 inches of chain pass by. It's going to go around, what did I just say? 3 inches around. So it'll go around 4 times. So in this case, these two have the same linear speed because they're both moving at the speed of the amount of chain pushed through has to stay the same, but it means the back one is going to be spinning faster. They'll have different angular speeds. So here we have the same, in the merry-go-round, we have the same angular speed, different linear speed. In these attached gears, we have the same linear speed, different angular speed, right? In bikes, this is what we use to make biking easier and harder depending on how we set those gears up, right? So let's look a little closer at these relationships and how they're connected and then do some examples. So for instance, let's say, what was it? Oh, I want to say linear speed we measure, we often use V, and this is going to be distance over time. So I'm using S here just to be some distance. Well, angular speed is going to be how much angle changes over time, right? So it's a linear measurement versus an angular measurement. And the symbol that we often use for this angular speed looks like a little W, but it's the Greek letter omega. When you see it in type where things are a little neater than my writing allows, you can see the difference. So that's the lowercase omega from the Greek alphabet, okay? So let's see, what can we do here? Notice that we can take, we'll go back to our relationship, a previous relationship, S equals R theta, right? This was the distance, the arc length is equal to the radius times the angle that's subtending that arc length. And we can use this new angular speed idea and replace theta. So with a little bit of algebra, this can be rewritten as theta equals omega times time. So we can replace theta with that. And now this thing is S. So we'll have V equals, I'm using this formula here and replacing S with R omega T. This is over T, the T's cancel, and we have R omega. So let's rewrite this. This is our relationship between linear and angular velocity or speed. If we have the angular speed, the linear speed is that times the radius, right? So what we mean by that, for instance, if we know the angular speed of this merry-go-round and we want to know the linear speed of this child, how much distance is that child covering per unit time, we would take that angular speed and multiply it by the distance from the center. So let's do that example and see how these two children compare. Let's give a little more detail here. Let's say we have, so we've got two children on a merry-go-round. So I'll put it merry-go-round. There's probably hyphens in there. On a merry-go-round, spinning at, what did I say? Let's say spinning a full rotation in 3 seconds. Okay, so in 3 seconds, they go all the way around, right? I guess let's go a little slow. Maybe they're little children. So we'll say child A, I should have given them names. This sounds very clinical. Child A sits 2 feet from the center. Child B sits 5 feet from the center. Let's compare their speeds, their linear speeds, in feet per second. Okay, so that means we're going to, we want to find V for each child, which means we first want to find omega, the angular speed. This is again, notice we're dealing with radians per second. As soon as we used this relationship here to derive all of this, we have to be in radians, and we were given our rotation in or our angular speed in rotations per second. In other words, we need to do some conversions. So omega is going to be, oh, there goes my crazy pen again. All right. Okay. So our angular speed is 1 rotation per 3 seconds, right? And I want to get rid of seconds and get towards I want to get rid of rotations and go to radians. So I want to say, I want to multiply by 1. So 2 pi radians is equal to 1 rotation, right? Because 2 pi is all the way around, 1 rotation is all the way around. So just multiplying across now, our rotation units cancel, and we've got radians per second. In this case, it'll be 2/3 pi rad per second. Okay, so there is our angular speed. So then the linear speed of these two children, child A, oh, it's doing it again. Maybe it's time to get a new pen. Sorry about that. It does a thing where it starts writing whether I'm touching the pad or not, if I'm within about an inch. Okay, child A, we're just going to take the radius. So this child is 2 feet from the center, multiply it by omega, which we now know to be 2/3 pi radians per second. Multiplying across, we get 4/3 pi feet per second, right? Which is about 4.2 feet per second. Child B, sitting 5 feet away, we'll take 5 feet times 2/3 pi radians per second is going to be 10/3 pi feet per second, which is approximately 10.5 feet per second. Oops. And this should go right along with our intuition. Looking at this terrible sketch I did here, you can see that in the same amount of time, because in 3 seconds they both go all the way around, the inner child, child A, has traversed this smaller circle, while the outer child, child B, has traversed this larger circle. And if you've ever been on a playground, merry-go-round, you've experienced this. If you move towards the center, it's easier to stay on. If you move to the outside, you can really start to feel how much you're being accelerated, changing your direction as you move. Okay, there's one example, the connection between linear and angular speed. Let's do one more. Like one I did in my last video where we were walking around the equator, let's do something with Earth. And because the universe is complicated, we're going to approximate a bunch of things to make this doable. So let's try to make an approximation for the Earth's linear speed around the sun in kilometers per hour. So Earth's linear speed in kilometers per hour. Okay, so we need a couple of things. The Earth's distance from the sun is about, so I'm using that little swiggle to be approximately 150 times 10 to the 6th kilometers. So about 150 million. Now, this is a huge approximation. The orbit isn't even a circle. It's more of an ellipse, but we're approximating things. So we're taking its like average distance from the sun and pretending that we're traveling in a circle. So this is just really going to give us a good an approximation. We also know that it completes we get a complete orbit once all the way around in 365 days. Again, there's a little bit extra there, but we're gonna keep this as our approximation. Okay. So what we need to do, remember, we're going to use V equals omega r. We have the radius, or our approximate radius is this value. We have an omega. This right here is giving us an angular speed, how many rotations per unit of time, but we need to convert this to radians. So let's do that. One orbit in 365 days. I'm going to multiply it by 1. So the first one I'll multiply by is to get us into radians. So 2 pi radians is one orbit, right? One complete circle around the sun. The circle is in quotes since it's not quite a circle. I also want to convert this into the right units of time. We have it in days. I want it in hours. So I can multiply by 1 again by taking the fraction 1 day over 24 hours. Since those are the same thing, that fraction is equivalent to 1. I'm not changing anything about this. So this is my omega value. So we multiply across and we end up with pi over 4,380 radians per hour. Okay, and that is our angular speed, the angular speed or the approximate angular speed of the Earth around the sun. Okay, so now it's a simple matter. We multiply, we take V, we multiply this omega, pi, over 4,380 radians per hour. And we're going to multiply it by the radius, which I have here is 150 million kilometers. And we end up with 110 rounded, 110,000 kilometers per hour. All right, and so that's the linear speed with which we're all moving through, the approximate linear speed with which we're all moving around the sun. Maybe we'll put this in something more familiar for some of us, 110,000 kilometers per 1 hour. Multiply it by 0.621 miles per 1 kilometer. Kilometers cancel, multiply across, and we get 68,310 miles per hour. Okay, so almost 70,000, about 70,000 miles per hour. It's pretty approximated value we're getting here, but still gives us some notion of what's happening out there, or I guess right here. Okay, that's it for now. Thanks everybody. I will see you next time.